So let's go look at this thing. So now my job here is to interpret this. And I want to go through 4 things. Okay. So there's 4 interpretations of this thing. So let me find my mouse. You know, you always hear me say, let me find my mouse. What I have is I have 2 screens. I have my computer screen and then I have my tablet. And sometimes I move the ball off the screen and then I can't find it. Maybe that's what happens when you get as old as I am. You start to lose your mind. Here we go. So now we want to interpret N2L. And we'll do this over 4 things. The first thing that we want to do is we want to talk about the units of measurement. And probably the simplest way to do this is to sort of like talk about my weight. So I'll say this is Carlos's weight. Well, one way that by the way, I should also say that weight is a fancy word for force of gravity. The force of gravity is the force that acts on your mass, and that's what we call weight. So when I look at my weight, there's 2 ways to write down the weight. Well, I could say that I weigh 210 pounds. So when you look at this 210 pounds, this is really the English system. Now, what's terrible about the English system? They're made up of units of 16, right? There's 16 ounces to a pound. So the core fundamental unit is 16. That is not a very good system. I mean, even though we have 10 fingers, 10 toes, why didn't we use a system of 10 units? And what we find in them, so when I go and I reinterpret that weight, and I look at this in terms of the metric system, this is 200 newtons. So when I look at this guy here, this is made in, this is written in the metric system. So instead of using units of 1/16, we use units of 1/10. So every time we make a calculation with the units of 16, we have to really be careful with our units. But with units of 10, it's really easy to move the decimal point. And the way I interpret the English system and the metric system, even though I think the units system for the metric is better, I really can say that there is an analogy between these two as the exchange rate of money. And what I mean by that is that I could imagine that there's an exchange rate of dollars versus, let's say, Mexican pesos. And when you look at this thing, what you find here is that, so if I have $5, I mean, I can look at the exchange rate and I get the exact same amount in pesos, right? There's a rate that's set, but it's not that one is better than the other. It's just that there are 2 exchange rates. For science, the metric system is far superior. And I wish our country would change to the metric system because it's easier. So here's what we find. So when we look at the metric system, we find that there's a unit of force. That unit of force is what we call a Newton. And we typically write a Newton with the symbol N. And then we have a second mass set. And the second mass set is known as a kilogram or kilo or kg. And so what you're finding here is that this is the units that science prefers to use. And so these are the units that I will use in this class. Again, it makes it a lot easier if you use this. So how much force/weight is 1 Newton? So what you find here is that we probably need a conversion here. So this is what I know. So if you have 1 Newton of weight, which we typically write that as 1N, this is about the weight of a stick of butter. Now, is that a good way to look at it? Probably not, but that's what it is about. And what you find here is that 1 Newton, which might be more useful, excuse me, not 1 Newton, but 1 pound, this is what I use most of the time. 1 pound is about 4 Newtons. It's actually 4.25 Newtons. So these are the things that I'm going to use to try to get you to get a sense of what is going on. So if you look at my my weight, I would take my weight. I weigh 210 pounds. And what would I do if I wanted to convert it into newtons? What I do then is I multiply that by 4. And if I multiply that 4, I get 840 newtons. And you can see that it's pretty close to that. It's really, really, really close. So if you weigh, let's say 100 pounds, then that means if I multiply that by 4, it'd be 400 newtons. Okay, let's move on. Let's go to the second one. Now remember what I said here. This is the law of common sense. So if this is the law of common sense, then I should be able to show you that this is common sense. So before I want to talk about acceleration now. And what I know about the acceleration is proportional to the net force. To make sure that we all speak the same language, what does Newton's second law tell us? Well, it tells us that the acceleration is equal to the net force divided by the mass. So when I say that the acceleration is proportional to the net force, what that means here is that I'm going to ignore the mass, okay, by making the masses the same. So what we say here is that now this is our focus. So then what we say here is that this is really says that the acceleration is what? Is proportional to the net force. So if I look at this word proportional, what we do here is that now we replace it with this symbol right here, little fish symbol. So if I was to rewrite this thing, I would then say that the acceleration is proportional to the net force. And what this tells me here is that if you push harder on an object, the object the object will move faster. That's what this tells me now. So if I look at this thing, this is what this is telling me. But these are just a bunch of words. What we want to do is that we want to do pictures. Pictures are worth, right? They're worth a lot. So let's look at this thing here. So imagine that I have two boxes. Now remember, the masses have to be the same. The only way I can ignore the mass if they're the same. So let's draw two boxes. And here they are right here. And what I'm going to do here is that I imagine that they're on some surface. So when I'm looking at the surface right here, I know that they're going to be sliding. So now what I'm going to do here is that I'm going to push on them. So if I do that, here's what I'm trying to say. If I apply a small force to this versus me applying a bigger force, which one's going to move away faster? Of course, the one with the bigger force. So if I come in and I draw this thing, what this tells me here is that now, if I look at the accelerations, this tells me that this guy is just going to speed up just a little bit. This guy is going to speed up more. So what we say here is that the smaller force causes a smaller acceleration. So how do I write this? Well, I go, hey, if I have a small force, then I'm going to get a small acceleration. On the other hand, if I have a larger force, it causes a larger acceleration. I pushed harder, right? So if I pushed harder, it's going to speed up to a higher speed. That's common sense, right? That's common sense.